So, I come back to this figure. So, let us consider B. B got halted here, but you see in the very same cycle this fellow D is consumed. Okay, D is consumed. I do not need to propagate it further down the line. So, R2 output was free, or R3 input. R3 input is free. From R2 output, I will take it to the output port. I will not give it to the input of R3 because this is over, right. It will go to the output port by a switch. It will not come to the input of R3, which means input of R3 automatically gets free, and that is happening because the number of register is chosen to be 4, which is obtained from the lifetime chart, which assured us that 4 is enough to store all live variables in every cycle, which means if I am not reaching the end, somebody else will be consumed, will be over. So, a new register input will be free, and that is R3 here. So, R3 input becomes free. So, I will give it to the R3 input here, and it will continue like this. So, it comes to 6 to 7, but what is this fellow? This fellow is B. B is from 1 to 7, fine, I reach the end. So, this is B. Similarly comes C. C has reached here, but I am sure somebody will be available. Some register input will be available where I can give, and it can proceed down the line. Now, look at this G. G was supposed to go to the input of R1, but G is born and dead in the same cycle. So, G is born. The moment it is read, I will send it to the output port by a switch. I will not take it to the input of R1, which means input of R1 is free in this chain of registers. So, it will be taken like this and given to the input of R1, so that it will continue in the same manner. C goes up to 10, so it will continue. You see, all these boxes are free for it. Okay. That is again happening because number of registers is enough. In every cycle, I do not have any storage problem. Okay. So, it is stored by R1, then R2 available, then R3. Somebody or other will be available down the line. The way we carry out, it is following a sequential process from R1 to R2 to R3 to R4, whenever it is requiring that that many cycles. So, it goes from R1 to R2 to R3 to R4, and the boxes are available. Okay, I just gave it to the appropriate input, and from that onwards, like it came to the input of R1, and from that onwards, in every cycle some boxes are free. The boxes are free down the line. Okay, so it goes from R1 goes to R2, R2 to R3, and so on and so forth. Okay, because that is the general direction of movement of data from R1 to R2, R2 to R3, R3 to R4, like that. Okay, it reaches 10, and C is from 2 to 10. So, I have found the end. Okay. Then one more fellow is left, that is F. F is from 5 to 11. Now, here you see this fellow is over, which means at cycle 9 R2 output goes to the output port by a switch, it does not go to the R3 input. So, from R4 I bring it to the input of R3 and moving forward again. You see these boxes are open. F is from 5 to 11. So, it will go from here to 10, 10 to 11 and done. So, F, all right. But one thing you see, from 0 to 8, this was say LH cycle. Next cycle starts from here. So, it will take, I will require new, I will be reading, system will be reading a new A, that is maybe A prime, new B, B prime, new C, C prime, new D. But will they give rise to any overlap? Answer is no, because you can easily see A prime will be born here, it will go like this. I am just following this route. Dot 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 dot. B prime is born here, it will go like this. C prime born here, it will go like this, and so on and so forth. So, these fellows, I am just hashing them actually. they are not overlapping with this. They are not coming in conflict. Okay, that is 4 registers are good enough to store variables of this LS cycle and live variables from L plus 1s cycle, okay, in any system cycle. Like system cycle number 9, I have got H coming here, I have got G coming here, I have got F, but I have got also A prime, 4 are required. Similarly, in cycle 10, I have got A prime coming here, B prime and 2 fellows from the previous one. This guy which is I, this guy which is C. Okay. So, 2 fellows from the previous one, previous input, and 2 fellows from the current input, but total is 4. So, you see 4 is that magic figure. Since I have chosen that, I am never in short supply of any registers, even when I am considering the overlapping zone, where in any horizontal line, this boxes, horizontal row or any row, I have got some boxes filled up by previous variables like A to I, part of them, some of them, and some boxes filled up by the current variables, that is from A prime to I prime. Okay, but there is always no conflict. Some boxes are available for the first category, some boxes are available for the second category, whereas 4 is good enough. We obtained it from the lifetime chart. Okay. If this be, then how to have a circuit for it? Okay. Okay. Let me see, I am in need of some space. I have R1, R2, R3, R4, and input is coming here, input. You can see one thing, and output is here. You can see one thing, input always, except for this line number 6, input is always going to R1, input of R1. Only in cycle 6, the input data directly goes to the output, right. So, from input, one line goes to the output and output has a switch, output will touch it at 9L plus 6, I am just writing 6, okay, but actually 9L plus 6. So, output port, here is a switch, it will touch this at 6. So, at 9L plus 6, whatever be the input which is G, that will go to the output. R1 at this time at cycle 6, input of R1 will come from this here, that is R4 output, look at the red line. So, R4 output will be fed back to R1 input at cycle 6. So, it will be switching, it will touch it at 6 and touch it at the other cycles, you know. I am not writing them, if I write 6 and I do not write anything, but or maybe for your sake I write 0, 1, 2, I mean there is no space. So, I am orally telling you at cycle 6 R1 touches, R1 input touches this line, at all other cycles, that is 0, 1, 2, 3, 4, 5 and then 7, 8, it touches this one. This is the meaning of it. Okay. Maybe the switch I redraw, switch is here, it will toggle between either this or this. It will touch it at 6, 9L plus 6, in all other cycles it will touch here. When it touches at 9L plus 6, input takes this path, it is born and dead, it goes to the output. But in all other cycles it touches input line. So, input goes to the R1 input. R1 input you can see is always going to R2 input. Look at these, here, okay. That means R1 to R2 there is a permanent correction. Whenever whatever be there in the R1 output, that will always go to R2 input. R2 output, now look at this R2 column. R2 output, here it is going to in cycle 5 fellow D. This is consumed, means from R2 output it will be sent back to output port, and also here. Okay. From R2 output in cycle 9 it will be sent back to output, right. So, R2 output this will go here at cycles 5 and 9. Now, I tell you one thing, actually it is 9L plus 5 and 9L plus 9. Now, I prefer this notation, but the notation followed by K.K. Parhi in his book and also in papers is this: whenever it is say 9L plus 9, it is becoming say 9 into L plus 1. So, as though it is 9 into L plus 1 plus 0, that is in the 0th cycle, 0th system cycle for the next input cycle. That is basically 9, you take modulo 9, that is 0. So, instead of 9L plus 9, he writes is 0. So, he writes is 0 and 5. I prefer 9L plus 9, but since it is 9, 9 modulo 9 is 0. If it is 10, 10 modulo 9 is 1. If it is 10, it would become 1. So, for L plus 1th cycle, input cycle, it will be the 1, system cycle 1, but input cycle goes to L plus 1. That is 10, if it is 10, 10 modulo 9, that is 1, 1 would have come here. Okay. And I would have written 1 here instead of 0. It is a modulo notation. So, if I follow modulo notation, it is actually 9L plus 9, but which you can also write this way. 9 means 0 to 8, those are the system cycles for one input clock. 9 means I am entering the 0th system cycle of the next input clock, L plus 1th. That is why we write 0 here. That is the style followed by Parhi and others, sorry. Five remains 5 because 5 modulo 9 is 5. The moment you exceed 8, you become 9. 9 is effectively 0 for the next input cycle, that is 9 modulo 9 is 0. When it is 10, 10 modulo 9 is 1. When it is 11, 11 modulo 9 is 2, like that. So, for this diagram, I am following this notation. Okay. Or I mean, I am doing it so that you are not in any confusion when you read K.K. Parhi's book. But if you are clear about what I said just now, then I can, if you permit, I can stick to my notation where I do not replace 9 by 0, I just write 9 here. Okay. Maybe I do that because I have already told you the meaning, so that if you read the book, you will not find 9 here, you will find 0, but you will understand what it means when you see this lecture. I am writing it as 5 and 9. In K.K. Parhi's book, 9 will be 0. Okay. Well, because he is following a modulo notation. So, let me stick to my notation 5 comma 9. All right. So, that is from R2 output. And when R2 sends them, that time who comes to R3 input? R4 output goes to R3 input. Again here R4 output goes to R3 input. What are the cycles? 5 and 9. So, R4 output comes here, and in 5 and 9 this guy touches this, otherwise it touches this. All right. It touches there 5 and 9, otherwise it touches this in all other cycles. And R3, R4 you can see there is a direct path. Whenever there is R3 output that is always given to R4 input, the line continues in all of them, it continues like this. Okay. That means R3 to R4 there is a direct output, and R4 output here, here, they go to output port. So, in which cycles? 4, 5, just a minute. So, here 4, then here 7, 4, 7, 4, 7, then 8, up to 8 is fine. Then here 10, 10 in Paris book will be 10 modulo 9, which is 1. So, he will write 1, but I am writing 10. Then 11, 11 in Paris book or in some other literature will be 11 modulo 9, which is 2. So, they will write 2, I am still writing 11 here. And similarly 12 in their book, in his book will be 12 modulo 9, which is 3, but I am writing 12. All right. So, this is a circuit. So, this gives you a fairly good idea about how to carry out lifetime chart after doing lifetime analysis, and once you do the lifetime chart, you know the minimum number of registers required. Then you follow this forward backward data allocation table, this method of moving the data and still storing them in the system and develop a circuit for it. This is the whole journey for minimizing the number of delay registers, okay? Because I am always hitting on minimum number of delay registers required. That is why delay is optimized. Now, I consider a more relevant example, that is the digital filter we started with in the very beginning of this folding section, folding, we started with digital filter. I go back to that example. Remember, quickly I draw that figure again. Adder 1, adder 2, adder 3, this same old stuff 4, multiplier 5, multiplier 6, multiplier 7, multiplier 8. Okay. The schedules were this, there is the folding sets SA was 4231, SB, sorry, SM multiplier that was 5867. Pipeline latches, PA was 1, PA was 2, okay, and period was 4. That is, you read the input cycle, system is working at 4 times faster than the input because folded by 4. Then after 4 system cycles, another input comes and new set of variables will have to be stored also. So, there will be overlap between 2 or more than 2 cycles, and we still have to carry out storage of all the live variables in this filter. Now, you remember we obtained those folded delay, the delay figures after folding. DF, I am just writing from there, copying from there. DF 1 to 2 we had 1, 1 to 5 we had 0, 1 to 6 we had 2, then DF 3 to 1, that was 0, DF 4 to 2, that was 0, DF 5 to 3 also 0, DF 6 to 4, 0, DF 1, okay. This was the thing. Now, let us carry out first lifetime analysis, identify the variables. Adder 1, what is this 4 adder? 4 adders are nothing but they are replaced by one hardware adder unit of this type. That is, there is an adder, actual adder, it will pipeline by one latch that I am showing separately by one delay. The output, this side is switched, this side is switched. There are lines, input lines, there are lines. A particular cycle, say let us consider adder 1. Adder 1 has cycle, schedule 3, 0, 1, 2, 3. So, at schedule 3, it will touch, if it is adder 1, if it is input, okay, at schedule 3, let me erase this. At schedule 3, it will touch that particular line. What line? In. At schedule 3, because in is entering adder 1. At schedule 3, this fellow will work for adder 1. So, it will touch in and it will touch some other appropriate line here. Then it will carry out a summation and it will get delayed by one cycle. So, adder output, the output is born, but internally also delayed by one cycle. So, it was born in what schedule? At cycle 3, because 0, 1, 2, 3. 3 is the schedule of adder 1. So, at cycle 3, this fellow is touching the appropriate inputs like in from here, carrying out the job of adder 1, okay, but there is an internal delay that is for pipelining. So, at schedule 4, that is clock 4, the adder output is coming in the system. That means the adder output, adder 1 output is born in not cycle 3, but cycle 4 because of one more delay inside. So, N1, I call it N1 for the N for node, N1 there is a node output 1, it is born in cycle 4, and then you see 1 is required to go up to 2, I need 1 delay, 1 to 5, 0 delay, same 1 goes to 6, needs 2 delay, 1 to 7, 3, 1 to 8, 5. That means node 1 output needs to be delayed maximally by 5, which will take care of 2, 5, 6, 7 all. Okay. So, I need to store N1 in the system for 5 cycles. So, if it is born in 4, it should go up to 9, 4 to 9. Okay. So, that 1 to 2 done, it requires only 1 cycle of storage, 1 to 5 done, no cycle of storage required, 1 to 6, 2 cycles of storage required, 1 to 7, 3 required, 1 to 8, 5. So, I will take, because the variable is common, N1, 1 is common for all of them. So, I take the maximum, that is 5. So, it is born in cycle 4, so delayed by 5. So, 4 plus 5 is 9. So, from 4 to 9, it has to be 4 is born and 4 to 9 is the journey in the system. It has to be stored, it has to remain stored, it has to remain alive in the system from 4 to 9. Okay. Then comes N2. N2 there is no problem, N2 is a node output. Okay. N2 adder 2 schedule is 1, that time it is carrying out the job of addition, 1 more delay. So, at cycle 2 the output is formed and it is not required to be stored. So, it is 2 to 2. Okay. Remember, schedule is 1 because there is node 2 and 1 more delay inside. So, N2 output is formed at cycle 2 and consumed that time only because it is not entering the filter again. So, consume that time, no need to store. N3 schedule is 2 and add 1 more delay. So, born in cycle 3 and look at here, 3 has only one line, 3 to 1, 0. So, born and consumed in the same cycle. N4 is adder output 4, 4 schedule is 0 and 1 delay inside. So, it will born in 1, but it will go up to what? 4 to 2, 0 delay. So, born in cycle 1 and consumed also cycle 1, sorry. Okay. Then N5 multipliers. N5, 5 schedule is 0, but there are 2 delays inside. So, born in 2 and then 5 to 3, 0 delay. So, 2 to 2. N6, 6 schedule is 2 and 2 more delay inside. So, born in 4 and 6 to 4, 0, there is the only thing 6 to 4, 6 goes only to 4. So, 4 to 4 because 0 delay, no need to store. N7, 7 here schedule is 3 and 2 more inside, 2 more delays inside. So, 3 plus 2, 5, in cycle 5 only it comes up. Okay. And 7 to 3, 1, so 5 to 6, cycle 5 born, delayed by 1 cycle to be consumed at node 3. So, that is 5 to 6 and N8, 8 schedule is 1, 2 more delays inside. So, multiplier output comes out at cycle 1 plus 2, 3 and 8 to 4, 1. So, 3 it is born, 1 cycle of delay. So, 3 to 4. Okay. Using this, I can carry out the lifetime chart. Sorry. So, I go up to 9. because in this column highest figure is 9, okay, 9. So, and I write here N1, N2, N3, N4, N5, N6, N7, N8, N9 and number of life variables, all right. Okay, start with N1. N1 born in 4 goes up to 9. So, N1 goes born in 4 goes up to 9. Then N2, 2 and 2. N2 born in 2, consume that time, no need to store. N3, 3 to 3. N4, 1 to 1. N5, 2 to 2. N6, 4 to 4. N7, 5 to 6. N7, 5 to 6. N8, 3 to 4. There is no N9, I wrote wrongly, there is no N9, 3 to 4. All right. And what is the period? Period is 4. So, this is one period 0 to 3, 4 to 7, 8 to 9. First, let us consider one cycle only. So, here 0, here 0, here 0, here 0 because they are just born, here 1 because this is to be stored. And this is born and dead, so they do not count. 1 is required here, none is required here, 1 is required, 1, 2, 1 required here, 1 required here, 1. Now, what I do is, from this 1, you go back by 4, so 1 plus 0, 1. From the 1, you go back by 0, by 4, so 1. From this 2, you go back by 4, so okay, that is 0 again, and lastly from this 1 you go back by 4, so again 0, 1. Now this 1 you first go back by 4 here, 1, and again go back by 4, 0. So, 1 plus 1 plus 0, because here 2 overlaps would come. Something which is getting started here, something which is started here, and one more. Okay. And now again 1 here. So, you go back by 4, that is 1, 2, 3, 4, this 1, and again another 4, 1, 2, 3, 4. So, 1 plus 1 plus 0. So, this is 2, this is 2. All right. So, you get the figure 2 because there is a maximum. So, maximum number of live variables is 2, which means I need 2 registers R1 and R2 to carry out the storage. This is a lifetime analysis and then lifetime chart. Then we will use 2 registers R1 and R2 and follow that forward backward data allocation methodology, okay, and carry out the storage and then develop a circuit, which will be done in the next class. Thank you very much.